We built computers to expand our brains. Originally, scientists built computers to solve arithmetic, but they turn out to be incredibly useful for many other things as well. Running the entire internet, lifelike graphics, artificial brains, or simulating the universe. But amazingly, all of it boils down to just flipping zeros and ones. Computers have become smaller and more powerful at an incredible rate. There's more computing power in your cell phone than there was in the entire world in the mid-1960s. And the entire Apollo moon landing could have been run on a couple of Nintendos. Computer science is a subject that studies what computers can do. It's a diverse and overlapping field, but I'm going to split it into three parts: the fundamental theory of computer science, computer engineering, and applications. We'll start with the father of theoretical computer science, Alan Turing, who formalised the concept of a Turing machine, which is a simple description of a general-purpose computer. People came up with other designs for computing machines, but they're all equivalent to a Turing machine, which makes it the foundation of computer science. A Turing machine contains several parts: an infinitely long tape that's split into cells containing symbols. There's also a head that can read and write symbols to the tape, a state register that stores the state of the head, and a list of possible instructions. In today's computers, the tape is like the working memory or RAM. The head is the central processing unit, and the list of instructions is held in the computer's memory. Even though a Turing machine is a simple set of rules, it's incredibly powerful, and this is essentially what all computers do nowadays. Although our computers obviously have a few more parts, like permanent storage and all the other components. Every problem that's computable by a Turing machine is computable using lambda calculus.
Ya, saya mau tahu sedikit ya Pak tentang apa yang dijelaskan di Map of Computer Science ini. Ya kayaknya sih kita jadi mahasiswa harus lebih belajar lagi tentang perhitungan kayak kalkulus itu kan bakalan jadi dasar buat kita paham sama apa yang dilakuin komputer kayak bahasa pemrograman, misal kayak algoritma, terus pasti di algoritma tuh ada macam-macam kayak bahasa pemrograman atau yang biasa kita belajar itu kayak Python, PHP, gitu-gitu ya kayaknya. Itu aja sih Pak, saya sok tahu dulu ya. Lanjut.
Which is the basis of research in programming languages. Computability theory attempts to classify what is and isn't computable. There are some problems that, due to their very nature, can never be solved by a computer. A famous example is the halting problem, where you try and predict whether a program will stop running or carry on forever. There are programs where this is impossible to answer by a computer or a human. Many problems are theoretically solvable, but in practice take too much memory or more steps than the lifetime of the universe to solve, and computational complexity attempts to categorize these problems according to how they scale. There are many different classes of complexity and many classes of problem that fall into each type. There are a lot of real-world problems that fall into these impossible-to-solve categories, but fortunately computer scientists have a bunch of sneaky tricks where you can fudge things and get pretty good answers, but you'll never know if they're the best answer. An algorithm is a set of instructions independent of the hardware or programming language, designed to solve a particular problem. It's kind of like a recipe of how to build a program, and a lot of work is put into developing algorithms to get the best out of computers. Different algorithms can get to the same final result, like sorting a random set of numbers into order, but some algorithms are much more efficient than others. This is studied in algorithmic complexity. Information theory studies the properties of information and how it can be measured, stored, and communicated. One application of this is how well you can compress data, making it take up less memory while preserving all or most of the information. But there are lots of other applications. Related to information theory is coding theory. In cryptography,
jadi yang dipahamin juga di information theory juga kan kita udah pernah belajar kayak bubble sort, terus sorting sort itu di struktur data ya, berhubungan lagi dengan angka-angka ya. Jadi ya kayaknya kita harus sedikit paham tentang, atau lebih paham deh, harusnya lebih paham lagi sama bahasa pemrograman yang di dalamnya ada hitung-hitungan gitu, karena bakal kepake banget pasti, ya kan. Lanjut.
Cryptography is obviously very important for keeping information sent over the internet secret. There are many different encryption schemes which scramble data and usually rely on some very complex mathematical problem to keep the information locked up. These are the main branches of theoretical computer science, although there are many more that I didn't have time to go into, like logic, graph theory, computational geometry, automata theory, quantum computation, parallel programming, formal methods, and data structures. But let's move on to computer engineering. Designing computers is a challenge because they have to do so many different things. Designers need to try and make sure that they're capable of solving many different kinds of problems as optimally as possible. Every single task that runs on a computer goes through the core of the computer, the CPU. When you're doing lots of different things at the same time, the CPU needs to switch back and forth between these jobs to make sure everything gets done in a reasonable time. This is controlled by a scheduler, which chooses what to do and when and tries to get through the tasks in the most efficient way, which can be a very difficult problem. Multiprocessing helps speed things up because the CPU has several cores that can execute multiple jobs in parallel, but this makes the job of the scheduler even more complex. Computer architecture is how a processor is designed to perform tasks, and different architectures are good at different things. CPUs are general purpose, GPUs are optimized for graphics, and FPGAs can be programmed to be very fast at a very narrow range of tasks. On top of the raw hardware, there are many layers of software written by programmers using many different programming languages. A programming language is how humans tell a computer what to do, and they vary greatly depending on the job at hand, from low-level languages like assembly through to high-level languages like Python or JavaScript for coding websites and apps. In general, the closer a language is to the hardware, the more difficult it is for humans to use. At all stages of this hierarchy, the code that programmers write needs to be turned into raw CPU instructions, and this is done by one or several programs called compilers. Designing programming languages and compilers is a big deal because they are the tool that software engineers use to make everything, so they need to be as easy to use as possible but also versatile enough to allow programmers to build their crazy ideas. The operating system is the most important piece of software on the computer as it's what we interact with, and it controls how all of the other programs are run on the hardware, and engineering a good operating system is a huge challenge. This brings us to software engineering, writing bundles of instructions telling the computer what to do. Building good software is an art form because you have to translate your creative ideas into these logical instructions in a specific language, make it as efficient as possible to run, and as free of errors as you can. So there are many best practices and design philosophies that people follow. Some other important areas are getting many computers to communicate and work together to solve problems, storing and retrieving large amounts of data, determining how well computer systems are performing at specific tasks, and creating highly detailed and realistic graphics. Now we get to a really cool part of computer science, getting computers to solve real-world problems. These technologies underlie a lot of the programs, apps, and websites we use. When you're going on vacation and you want to get the best trip for the money, you're solving an optimization problem. Optimization problems appear everywhere, and finding the best path or most efficient combination of parts can save businesses millions of dollars. This is related to Boolean satisfiability, where you attempt to work out if a logic formula can be satisfied or not. This was the first problem proved to be NP-complete and so widely considered to be impossible to solve. But amazing development of new SAT solvers means that huge SAT problems are solved routinely today, especially in artificial intelligence. Computers extend our brains and multiply our cognitive abilities. The forefront of computer science research is developing computer systems that can think for themselves, artificial intelligence. There are many avenues that AI research takes, the most prominent of which is machine learning, which aims to develop algorithms and techniques to enable computers to learn from large amounts of data, and then use what they've learned to do something useful, like make decisions or classify things. And there are many different types of machine learning. Closely related are fields like computer vision, trying to make computers able to see objects and images like we do, which uses image processing techniques. Natural language processing aims to get computers to understand and communicate using human language, or to process.
Jadi dari rekayasa komputer ini, kayaknya sih banyak bahasa pemrograman yang harus dipelajari lagi ya. Terus kayak yang belum ditauin kayak SQL ya kayaknya, bukan SQL, MySQL, terus PHP, C++, Java itu kayaknya kita harus lebih kayak paham banget karena apa yang kita tuangin di program coding dengan logika kita juga tuh harus selaras gitulah. Udahnya kalau misalnya kita ngetik coding atau program ya sedikit mungkin biar nggak banyak error gitu kan, kita harus banyak belajar ya Pak ya gitu sih kayaknya ya kan. Terus ya penting juga sih ya karena biar kita juga lebih paham. Lanjut.
Large amounts of data in the form of words for analysis. This commonly uses another field called knowledge representation, where data is organized according to their relationships, like words with similar meanings are clustered together. Machine learning algorithms have improved because of the large amount of data we give them. Big data looks at how to manage and analyze large amounts of data and get value from it. And we'll get even more data from the Internet of Things, adding data collection and communications to everyday objects. Hacking is not a traditional academic discipline, but definitely worth mentioning, trying to find weaknesses in computer systems and take advantage of them without being noticed. Computational science uses computers to help answer scientific questions, from fundamental physics to neuroscience, and often makes use of supercomputing, which throws the weight of the world's most powerful computers at very large problems, often in the area of simulation. Then there is human-computer interaction, which looks at how to design computer systems to be easy and intuitive to use, virtual reality, augmented reality, and telepresence, enhancing or replacing our experience of reality. And finally, robotics, which gives computers a physical embodiment, from a Roomba to trying to make intelligent human-like machines. So that is my map of computer science, a field that's still developing as fast as it ever has, despite the fact that the underlying...
Ya, dengan menonton map of computer science, ya saya sedikit ngerti ya, kayaknya apa aja tuh yang dilakukan oleh komputer dan interaksi manusia dengan komputer itu kayak apa, terus mengkajinya bagaimana, mendesain sistem komputer sehingga mudah digunakan oleh manusia. Udah gitu aja sih, kayaknya cukup sekian dari saya, Lathifah dari 2 TIP 1. Assalamualaikum warahmatullahi wabarakatuh. Cukup sekian dari saya, Lathifah 2 TIP 1. Wassalamualaikum warahmatullahi wabarakatuh.